So I'm using that more often, kind of getting more comfortable with it. So here's our fourth problem. This one looked like a fun one. So we have a quadrilateral in a circle O. Okay, so we're going to want AB intersects CD. So I'm going to want to make it so that we can see that point. And then let me draw the center. So O is the center of C. And AB intersects CD at E. This almost looks like an isosceles trapezoid. So let's make it look a little less like that. AB intersects CD at E. P is, okay, so I draw the perpendiculars from P, or no, from E to BC and AD. Whoops. So that's P, and the other one's R. So here they skipped Q. Okay. ER is perpendicular. Yeah. EP intersects AD at Q. Okay. So yeah, now I draw the other intersection points. So this is Q, and the other one is S. K is the midpoint of QS. And we want to show EK and O are collinear. So this feels a lot like symmedians. I wonder if symmedians just like kill this problem. Let's see. So hide, 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 hide. And then I'll draw that and that. Okay. So let's see. Looks good enough to me. This almost looks like a right angle, which bugs me a little bit, but maybe that's a little better. Okay, so we want to show EK and O are collinear. But like triangle EBC is similar to EDA, and like P corresponds to R and S corresponds to Q. So this feels very, there's like a lot of structure here, right? So maybe, I wonder if we can use like the Gauss line. Let me see if the midpoint of PR is also collinear with those. No, it's not right. Sorry. Is EK, let me draw the angle bisector here. Okay, so EK is not the angle bisector. Yeah, maybe projective geometry can work here or something. How about completing the parallelogram ESQ? Interesting. So let me do that now. So EQSE prime. So that's another way to think about this. And I want to show, So we know that EK and E prime are collinear. It's all right. Sorry, guys, I'll be right back. All right. Let's see. This feels like a cool problem, but it feels like it has to collapse. I wonder if the gliding principle helps. Let's see. K is the center of PQRS. That is true. I probably should have noticed that. That is a very good observation. Okay. I wonder if E is on the radical axis of those two circles. Well, I don't think so, because that would mean PQDC is cyclic, which it's not. E on the polar of K. Let's check it out. GeoGebra actually has a nice polar tool. No. Yeah, to apply Ricard's theorem, it's like you need the intersection of diagonals. And yeah, we don't have like the intersection of diagonals here, but maybe there's some other way to figure it out. I don't know. So K lies on the perpendicular bisector of PS. Yeah. Maybe we could like use a homothety. So if you take the midpoint of AB, we want to show KOF is similar to KSE. I kind of like that idea. Actually, I'm not sure how helpful it'll be, but I don't know. Okay. So, I mean, we want to show O lies on the median of triangle ESQ. I wonder what the symmedian is. So, what is the symmedian of triangle ESQ? Let's see. If yeah, there's so many different ways to construct a symmedian, but I'll just pick a way. So that doesn't pass through D, obviously, but tangents. Okay, so this, I'm going to hide a bunch of stuff, but EF is the symmedian. Nothing looks super remarkable about it. Is that true? It feels very projective. Yeah, I don't see a solution right now, but it feels pretty projective to me. How do we apply Ricard's theorem? So for Ricard's theorem, often we need the intersection of the diagonals of a quadrilateral, but we don't quite have that here. So maybe there's still a way to get it to work. But I don't see it this second. Or Raffaello, do you see a way to use Ricard? Oh, maybe we can use Ricard on this. How do you use it? What quadrilateral are you using it on? Both. Okay. So yeah, it's about time I probably extend these two, right? So I can use Ricard's theorem. Okay, so basically, but I need like the intersection of the diagonals to use it though, right? That's the only thing that I guess bothers me a little bit. But maybe it's worth adding those in. I don't know. But is F, G, and H collinear? Yeah. Okay, that is pretty interesting. F, G, and H are collinear. And is that just obvious by Ricard's? Because FH is, we have EF is perpendicular. Yeah, I mean FH is perpendicular to EQ. No, not necessarily, but all right, see you, Hakan. Thanks for joining us. Providing F, G, and H is collinear finishes the problem. Okay, so let's see. What was I thinking? So what do we know? We know I'm pretty sure KH is perpendicular to EF. Is that a right angle? I'm not so sure. I think it should be by Ricard's. Yeah, it is. Okay. So yeah, I mean basically S is the orthocenter of EFQ, right? I'm sorry. Well, so I think is FH perpendicular to EK? I think that's true by Ricard's. Yeah, okay. So FH is perpendicular to EK. H is the orthocenter of EFK. And then FG is perpendicular to OE. So yeah, if we can show FG and H are collinear, that finishes it. Yeah, what Anmal just mentioned it in the chat. So yeah, he beat me to it. But so yeah, if FG and H are collinear, that would finish the problem. So Raffaello, do you see? Did you have a? Is that what point you got to, or did you see a way to show FG and H are collinear? Let's see. Can we use Pappas or something? I'm not sure. Feels a little bit like Pappas, doesn't it? I wonder if BGHC is cyclic. And then maybe like if we could use the radical axis theorem or something. No. So Raffaello, did you see a way to show FG and H were collinear? I think it's a good idea. But yeah, I'm still trying to see how to prove that. Angle chase GFB. Maybe. So one idea I have, if we drop the perpendiculars from G to BC and AD, and then we do the same for point H, and we show that those are in the same ratio, that would solve it. I think that could help. So like, if I can show that GI over GJ, then if I drop the same perpendiculars from point H, whoops, may have to zoom in a little bit here. Yeah. If I can show GI over GJ is HM over HL, then that would prove that they're collinear. I've seen that used before. So GI over GJ, that's the same as BC over AD, because those two triangles are similar. And then HM over HL That's PS over RC. Yeah, so that solves it pretty much. I feel like there might have been a simpler solution to this problem, but that works. Yeah. All right, so I'm going to start writing it up. Let me hide a few of the extra things. Okay, so let me try to see how I can make some room. Let's see. How do I make room? That is the question. It's a tricky, tricky question. How to make room for the solution. I do it like that. I think that gives me a good amount of room. So I kind of like that. All right. So I added in a lot of points here. So I will describe what those points are. Yeah, I'm just going to leave the figures as it's. So angle QPS equals angle QRS equals 90. Okay. Yeah, I'm still using Ricard's, but yeah, I'll just finish writing it up and then see what you have in mind. So angle QPS is equal to angle QRS implies that QPSR is cyclic. Cyclic with center K. All right. So then we could say let BD intersect AC at G. And let QS intersect PR at H. All right. And then by Ricard's polar theorem on ABCD, we have O8 and oh yeah, point F I'll introduce. So I don't think that wasn't a problem. So let BC intersect AB at F. Okay, so by Ricard's polar theorem on cyclic quad ABCD, we have OG perpendicular to EF. Is that what I was originally thinking? Or no, we want FG is perpendicular to OE, and that's also true by Ricard's polar theorem. So FG is perpendicular to OE. And then if we do it again, but on PQRS, then we have EK is perpendicular, or FK is perpendicular to KE. Right? Actually, I'm getting all confused, but I think that's right? FK is perpendicular to KE. Oh, this should be FH is perpendicular to OE. Wait, no, this, I'm so confused. FG is perpendicular to OE, and FH is perpendicular to KE. That sounds better. So then we want to show, oh yeah, you just helped me out in the chat. Okay, so then we want to show FG and H are collinear, because that would show that OK and E have to be collinear. And we could do that using the ratios, as I mentioned. So we'll say let I, J, M, and L be the feet of the perpendiculars as shown. And so, first of all, triangle GBC is similar to triangle GAD, and I corresponds to J. So okay, so basically GI over GJ is BC over AD. Okay. And then similarly, we have HM over HL is PS over QR. So the thing is, PS over QR is BC over AD, because P and S are basically, triangle EBC is similar to triangle EAD. So EBC is similar to EDA, and P corresponds to R, and Q corresponds to S. And so that means that PS over QR is BC over AD. And that means that GI over GJ equals HM over HL, which means that F, G, and H are collinear. All right. So Raffaello, was there like a faster way of thinking about this? And if F, G, and H are collinear, I'll just write it out here. And that means that E, K, and O are collinear. So Raffaello, was there like a faster way you were thinking of doing this than using these ratios? I'm just curious. What was your way? Type it out in the chat. I'm just curious. Okay, so D, C, H, and E are in harmonic conjugation. Okay. Oh, so since you're saying since D, C, since those four lines are in harmonic conjugation, and also the same with the other, like I think you mean like FQ, FP. Yeah, that makes a lot of sense. I did not think about it that way. All right. Well, thanks for the suggestion. Yeah, that's definitely a lot faster than what I had in mind. So I will move to the next problem. All right. So let I be the incenter of triangle ABC. And then I is the center. And we have a circle through B tangent to CI at I. And okay, so basically, I'm just trying to think how to do that. So I'm going to want to draw CI, and then I'm going to want to draw a perpendicular. And I want to see where the perpendicular bisector BI meets that. And that will be the center of the circle. Okay, so here's my circle perpendicular to BI, or tangent to CI at I. And then I'll do the same thing here. So I'm going to draw that circle. And we want to show that these circles intersect on the circumcircle of ABC. Okay, so I'm going to hide these lines. Okay. Interesting problem, kind of short. Maybe it would help to draw in these points. I'm not sure. If that point is X, is AX perpendicular to BC? That's interesting. I don't think so. Because, yeah, like if I do it like that, that doesn't look perpendicular. Let's see. So I'll call this O1 and O2. Well, no, those are the names of the circles, not the centers. Yeah, maybe, is this like the point of tangency of the mixed linear in circle? I think it is. 8? Actually, I'm not sure. Is it worth checking that? I'm going to check it just out of curiosity. Let's see. At that point is K, extend Ki. Oh yeah, we want to see if it meets at the midpoint of the arc. Sure looks like it. Yep. So that is the mixed linear encircled point. So could we show, yeah, can we show that sum two of the circles, so we can hide one and then the other argument's the same by symmetry. Can we show that those meet at the mixed linear point? Or we could let this be the mixed linear point, and then we want to show that it's tangent. That's probably the easiest way, right? Yeah, and then I think that proves it. Yeah, because it's just an angle chase. So yeah, if you draw the mixed linear incircle, then it's easy to show by an angle chase that it's tangent. This is a silly problem. But again, knowing mixed linears helps a lot. So, all right, so let's draw the mixed linear incircle. Okay, so I'll just start by defining these points F and G. Let CI and BI meet the circle at F and G. Okay. All right. And now I'm going to draw the mixed linear incircle. What's the best way to do that? So I'll just kind of do it like this. So if I do this, I'm kind of cheating here. So it should be the circumcircle of EHJ. Okay, so okay, it looks like there's two lines here. I don't know why it looks like there's, what's this other line? I do not know what this line is. Do you guys know what that line is? I'm just going to look at the definition out of curiosity. Oh, that looks like it passes through, let's see. That's the perpendicular through I. Oh, we never deleted that when we were creating the first circle. Okay. So I just deleted that there. I'm going to draw a segment here. So draw the A mixed linear incircle. Let it be tangent to the circumcircled ABC at J, and then let D be the midpoint of arc BAC. Okay, and then it's well known that DI and J are collinear, so see my video on mixed linear incircles for that. All right, and once we know that, so I claim that BI and J is the circle O1. So, and I can prove that by an angle chase. So I'm just going to draw in BJ and CJ, but basically, how was I thinking to do it? So angle BJI, that's angle BJD, which is half of arc BAC, and then we can use an angle chase to show angle BIF is that same measure. So angle BJI is angle BJD, which is half of, it's really half of arc BD, which is a quarter. By tangent circles, we know G, H, and J are collinear. Yeah, we do know that too. But it's really just an angle chase. So I'm just gonna, I think this angle chase is simple enough to show that they're tangent. So I'm just gonna do a little bit more, but yeah. So that's half of arc BD, which is a quarter of arc BAC, which let me just write it like this. So that's half of arc BA plus arc AC, and which is equal to angle B, or angle C plus angle B. Or wait, let's write it out like this. So that's which is equal to angle BCI plus angle CBI, which is equal to angle BIE. So this might not all fit on one line, probably won't. So break it up. All right, but sometimes it's just stubborn with breaking things up. Enrique, I think you pulled me away once to try to get it to break this into two lines. I forget though.
Yeah.
What's the, I guess, look at how bad that looks. I guess we could just live with this for now. Oh well. So basically, that means that the circumcircle Bij is tangent to Ci at I. So that means that the circumcircle of Bij is O1. And then similarly, the circumcircle of Cij is O2. And so therefore, O1 and O2, O1, O2, and ABC concur at J. I fix my dollar signs. Concur at J. All right, so we have one more problem. I like that I used mixed linear end circles, and I'm sure GeoGebra helped. All right, so this is the last one from South Korea that I have. So triangle ABC is acute. The orthocenter is H. Do we want to put A and B at the bottom and C at the top for this question? I'll just leave it like this for now and see. So H, and then we draw the circumcircle of ABH. And it intersects line BC at a point D. So I'm going to need to extend that. All right. And lines DH and AC meet at P. All right. And the circumcenter of ADP is Q. It's pretty random, but okay. It looks like it lies on AB, but maybe that's just a coincidence or maybe not. Okay, well, we'll try to prove that. Prove the circumcenter of ABH, which is point Q, lies on the circumcircle of BDP. Wait, what? Oh, the circumcenter of ADP. Oh, I'm sorry, not ADB. Oh no, Q is the circumcenter of ADP. Prove out the circumcenter of ABH. Okay, so we need another point. So what circle is that? C. So the center of C, let's call it E. We want to show E. We want to show EBDQ is cyclic. Yeah. Okay. So we want to show that this is a cyclic quad. It's interesting. And we don't know yet even that Q is supposed to lie on AB. I wonder if that's like obvious or something. D. So the circumcircle of ABH has the same size as the circumcircle of ABC. That's a well-known fact. So if you take the circumcircle of ABC and you reflect it over AB, you get that other circle. Just going to keep that in mind. I wonder if these two circles are the same size. Let's see if that's true or not. It kind of looks, no, that's a bigger circle. But why does Q why does Q lie on AB? It's interesting. Why does Q lie on AB? I don't know if that solves it. Yeah, I'm not sure. So we want to show EQBD is cyclic. I'm gonna erase some of the excess. There we go. And we draw on these feet of the altitudes. Hide. So EDB is isosceles, right? So if we want to show that this is cyclic, we want to show that so then that would mean that EBD is EQD. So it would mean that EQD is the same as EDB. And we can angle chase a lot of these. Yeah, so like we know angle ABD is 180 minus angle B. Yeah, I mean, basically, yeah, we should be able to angle chase all the angles of triangle EDB. So it's this Q point. That Q point is the key. Actually, I'm not sure if it is as easy as I thought to angle chase triangle EDB. So angle AHP is equal to angle B. I wonder if AHP is similar to ABC. No, I don't think so. But angle B is 34.9. That's 34.9. Isn't BQ perpendicular to isn't BP, no, BF is perpendicular to AC. It's just a weird asymmetric configuration. So yeah, the circumcircle of ABH intersects BC at D. Yeah, like what if we rephrased it? What if we let the circumcircle of EDB meet AB at Q prime, and then we want to show that Q prime is the circumcenter of ABP. I think maybe that would be easier. Maybe. Yeah, because I feel like this is just a weird. Yeah. Let's try it from the other end. So what if I redefine Q? I could call it Q prime later, but what if I draw the circumcircle of EDB? Is GF parallel to DP? I think that might be true, and if it is, I would imagine it's not. Oh no, I don't think so. No. So yeah, let's redefine things a little bit. Basically, I want to show that Q is the circumcenter of ADP. So Q would basically lie on, well, yeah. That's so random. So Q is the circumcenter of ADP. So what if I did this? Because we know that this circle is the same size as the circumcircle of ABC. So I wonder. That's kind of interesting. Although I think it might. So I, E, and H are collinear. I would guess that's not super hard to prove. And let's even do this. So the reflection of C over AB is point J, and IBA is congruent to ABC. So since IBA is congruent to ABC, you're saying I, E, and H have to be collinear. Yeah, no, IBA is congruent to ABC. Why does that mean I, E, and H are collinear? Is that obvious? IQ looks perpendicular to AB. Yeah, it is by symmetry because, or wait, I think I spoke too soon. Yeah, IQ Why did I think that? I wonder what is angle D is. No, I don't think that's the right angle. The reflection of the orthocenter in the midpoint lies on the diameter. So but which, so yeah, is this intersection point the midpoint of AB? No. The reflection of the orthocenter of ABI. Okay. So yeah, so if we take like the midpoint of AB and we reflect H over it, that would be the orthocenter of IBA. And so since EH equals EI and HJ equals JH prime, we have like a mid segment. I'm still not sure how. Is it obvious that IE and H are collinear? I guess if we draw the circumcenter, yeah, okay, because if we I guess here's kind of how I think of it. Yeah, because like, so ABCH prime is cyclic. So yeah, since CO and H prime are collinear, IE and H prime will be collinear for the same reason. Yeah, because H, yeah, H is the orthocenter of ABI. Yeah, I'll just delete that for now, but I see basically what you're saying. Whoops. So yeah, H prime is the orthocenter of triangle ABI. So if you reflect it across the midpoint of AB, that would be the antipode of I. Okay. All right. So we want to show that Q is the circumcenter of I forget now. Q is the circumcenter of APD. Can we at least show Q is equidistant from some of those 2 points?
Wait, what are you taking as Q now?
Oh, I defined Q to be the intersection of the circumcircle of EDB with AB.
Oh, I see.
Yeah, so I redefined stuff. We can try proving EQ is perpendicular to AD. That would work. And maybe that's an angle trace. So we want to show EQ is perpendicular to AD. We could try showing angle EQD plus angle ADQ is 90. How would we get angle ADQ? Yeah, ADQ seems tricky. Is Q? So this is an isosceles trapezoid, right? IDBA. So angle Q, we want to show angle QAI is angle QDI. No, I'm sorry. We want to show angle QAD is angle. It's so weird. Q looks closer to D than A, but I guess it's just my imagination. Doesn't Q, to you guys, doesn't Q look like it's closer to D than it is to A? I feel like it's an optical illusion. Right? So it does, yeah. So QAD is the same as BAD, which is, yeah, there's a bunch of equal angles here. BAD, probably because Q and A are two other points, J and G. Yeah. We aren't using that E as the center. Yeah. So EDB is isosceles, so I'm kind of trying to use that, but yeah, we do have to use that fact. Okay. But yeah, it's so weird. We're trying to show Q's the circumcenter, but I can't even show it lies on its equidistance from 2 out of the 3 points. Let me check something. Sorry. So I wonder if we can angle chase that QD equals QA, because QA or angle QAD is angle BAD, and angle QDA is BDA minus BDQ, and BDQ phrase it. So we want to show Q as the circumcenter of DAP, basically. That's kind of how I was thinking about it. I redefined Q to be the intersection of this circle with AB. And now I want to show that Q is the circumcenter of ADP. Let's see. But yeah, if you can think of a better way to rephrase the problem, I'm all for it. Is EF parallel to GP? It could be. That's EF. No. Is it parallel to, I don't think this is true either, but yeah, no. Maybe power of a point somehow. So surely is Q the X circle touching point of I'm guessing you mean of C, of the CX circle. Could be, let's see. But I feel like surely we should be able to prove QA equals QD. Like that can't be that hard. I don't think so. That would be the X. No. But yeah, I mean, so we start with the triangle ABC. H is the orthocenter. We take the circumcircle of ABH and it meets BC at D. And then we take the circumcircle of DEB and it meets it at Q. Surely there's got to be a way to prove that QA equals QD as a very first step. So basically, we want to show that angle DBQ is twice angle DAB. We want to show DQB is twice DAB, but DEB, yeah, okay. So I've proven that QD equals QA. That's just an angle chase, because basically angle DQB is the same as angle DEB, which is twice angle DAB. So from there, DQA is isosceles. We just have to show that now P also lies on that circle. All right. In fact, I wonder if point I is even necessary here. Okay, so is DAC isosceles? Yeah, I think so. Yeah, DAC is isosceles because this is an isosceles trapezoid. So yeah, DAC is isosceles. Yeah, that's not a bad idea to draw in that segment. Okay. So QA equals QD. Can we use an angle chase to show that those are also equal to QP? I think this might be chaseable. Let's see. So QAD is isosceles. So yeah, QH prime and E are collinear. Or I'm sorry, QE is perpendicular to AB. It's got to be a way to finish this. Because we know all the angles in question. So yeah, we have this isosceles triangle DAQ, and we let DH meet AC at P, and we need to show P also is equidistant from Q. But if we know angle ADH and we know angle A, it seems like Q should like P should be uniquely determined. Okay, so I think it might be angle chaseable, because if we can show angle APD is half of angle AQD, that would solve it. But angle APD is 180 minus DAC minus ADH. Okay, yeah, so let me start writing up the solution. So, whoops, didn't want to do that. I think we've got this. So this will be the last problem I do, but I'm going to try to write up the whole solution. So let me make some room. Let's see, how do I make room here? It's not easy. Just want to shrink the diagram overall. Okay. So here's my text. Let Q prime be the intersection of okay, so I'll just say let E be the circumcenter of ADH. And let Q prime be the intersection of EDB with AB. And then first we can do a little angle chase here. So angle DQ prime B is equal to angle DEB, which is twice angle DAB, which is so basically that means Q prime dA is isosceles. So okay, so we have Q prime D is equal to QA from that. All right, because this plus this is twice that. And then we can also try to show P is equidistant, and we can try to do that. What was my strategy? I wanted to show dPA is half of dQ prime A. I think that was my strategy. And dPA I can say is 180 minus, yeah. So we also have angle dPA is 180 minus angle DAC minus angle ADH, which is so DAC is isosceles, as we mentioned. So this is 180 minus, so 180 minus angle DAC is twice angle C, right? Because DAC is isosceles, so that's twice angle C minus an angle ADH is the same as angle ADH. And what did we want to show? We wanted to show that dPA was twice dQ prime A, or dQ prime A was twice dPA. So ADH is 90 minus angle A, so that's 2 times angle C minus 90 minus angle A. Okay. And let's try this. I'll just leave it like that for now. And we want to show that's twice angle dQ prime A. But we already found dQ prime B up here. So dQ prime A is 180 minus that. So that's 180 minus, what was my expression up there? 180 minus twice angle DAB. But DAB is DAC minus BAC. So that's 180 minus 2 times angle DAC minus angle BAC. And then, yeah, DAC we had up above here, right? So I'm just going to say, okay, we wanted to show that. I'm just going to say by some calculation here, because we're running out of time, I'm just going to say by some calculation from the above, angle dq prime A is equal to twice angle dPA. And so that means that Q prime is the circumcenter we can write DAC as 180 minus twice angle C. Yeah. So yeah, that's what I did. I'm just going to finish this up quickly. But so that means that Q prime is the circumcenter of dPA. So Q prime equals Q. I'll say Q prime equals Q is the circumcenter of dPA. And so that means that the circumcenter of ABH lies on the circumcircle of BDQ, and that solves the problem. All right, so that is it for today. So I am going to stop recording here, but I feel like this was an awesome session. I feel like we got through a lot of fairly tricky problems. So thanks, Anmal, thanks, Enrique, and everyone else participating, Raffaello. Thanks for helping out on a bunch of the problems. And I will see you all next time. Have a good day.